Okay, so quick review. That what we looked at yesterday was the first half of specific immunity. So on the left side of your paper, what we're talking about is a macrophage, and this is the common part. The macrophage swallows up the bad guys, chops them up, and displays their antigens, which is what we call marker proteins for bad guys. Docks with the helper T cell, releases some interleukin-1, activates that helper T cell. Now that's where the split happens. The split, we talked about how these cells can divide and sort of turn into, or you can think of it as them communicating and telling cytotoxic T cells what cells to attack. Now, they only really attack eukaryotic cells, so that's only good against protists, fungi, and your own cells that might be infected beyond health. Okay, so that's the cell-mediated side of it, right? Cell-mediated as in it's actually a cell going to do the stuff. Where we're going now is what we call humoral immunity. It's called humoral for like old reasons, because in old medicine it didn't work. They decided that diseases were caused by imbalances in different humors. One of those humors was blood. Anyway, what happens here is that your helper T cells basically tell the B cells what the antigens on the bad guys are. And the B cells are going to turn into, because of the interleukin-2, sort of an oversized cell called a plasma cell. The plasma cell is going to start spewing out antibodies. Antibodies are different than anything else in this system. Antibodies aren't cells. They really aren't even quite proteins. Here's what they look like. They are made of amino acids, but they're not really folded up much. Basically, we call this this is the light chain. Those are the heavy chains. The important part is an antibody, which is real little. They're little tiny fragments of amino acids. When the B cell makes them, it's making them according to the instructions from the helper T cell, right? As to what the antigens look like. So what these are, and they're these little Y-shaped particles, kind of a twofold action here. What they do is those ends fit, they're kind of like receptor proteins, except they just stick. They stick to the antigens on the bad guys. So as soon as a bad guy bumps into this thing, it's going to stick here, because it's got those antigens on it. And then another bad guy might stick here, right? And then another antibody, because your plasma cells are just flooding your blood with these antibodies. They're just coursing through your bloodstream. So you got maybe another antibody here, and another bad guy sticks here. So what you wind up with is sort of the bad guys start clumping up. The antibodies start to stick bad guys together. And if they're stuck together, they can't do much harm. Secondly, a cluster of bad guys stuck together with antibodies is like a big old kill me sign for the rest of your immune system. They come and they clean it up, right? So once you are making the right antibodies, you're going to win. That's going to be the end of the story. But they got to be perfect. Antibodies don't work unless they match the pathogen exactly. And it takes time for this whole system to crank up. Specifically, it tends to take about a week. So that's you being sick, right? When you're sick for a week, which is average, right? Maybe a little less, maybe a little more. That week is the time it takes to get all this stuff rolling. Right? It's you feeling bad because A, maybe your system is doing some stuff to fight the disease that doesn't feel good, but B, you're just waiting for this part of the system to catch up. And once you are cranking out antibodies and flooding your bloodstream with them, bad guys don't stand a chance. So sickness for us generally is just the lag time between infection and the humoral immune system working. What's nice is that once you do this, once you take the week to figure out how to make antibodies against this one specific pathogen, you don't lose it. You keep, your antibodies go away, they degrade, and most of your cytotoxic T and helper T and B cells, they go away too. But you keep a few. You keep some so that you don't have to spend that week again. You don't have to wait a week next time, okay? Memory T and B cells stick around. They keep your ability to crank up the humoral immune system. Doesn't mean you're never going to get that disease again. Your immune response is going to be quicker and stronger. Most of the time to the point where you don't even notice it. And here's where maybe the most important antiviral tool we have comes in, which is vaccines, right? We still aren't very good at curing viruses. Once you've got a virus, we're not very good at fighting that. But we have a system that has been invented that can pretty effectively prevent you from getting a virus if we know that virus ahead of time. And that is, how do we prevent someone from getting a virus? We vaccinate them. Do you know the story of the first vaccine? Dude's name was Edward Jenner, and the disease was smallpox. Maybe the worst, most destructive disease in history. I mean, it's got competition, but it's pretty bad. Airborne, kills like 30 to 40% of those it infects, and those two together are pretty devastating. But what happened was Dr. Jenner started looking at who gets smallpox and who dies from smallpox, and he found one group that didn't. One group that almost never got smallpox. Who was it, Amanda?
The people who milk the cows.
Yeah, usually women. They called them milkmaids. Milkmaids almost never got smallpox. And so he dug a little deeper and hung out with the milkmaids some and found that most milkmaids on their first, few weeks on the job got this rash and called it cowpox. And this rash would produce blisters, but that's about it. Like, didn't make them really sick or anything. And so he theorized correctly that the cowpox was giving these women immunity to smallpox because it looked enough like smallpox that it was able to generate the right immune response without actually giving them smallpox. And so what he started doing was just taking the fluid from the blisters these people had on their arms and sticking other people with a needle dipped in that fluid. And literally that was the first vaccine. That virus is actually named vaccinia. The cowpox virus is called vaccinia. And that's how vaccination started. Now, basically what happens is you need something that has the right antigens that are similar enough to the real disease, but that won't make you sick, right? It's basically a dead or different enough pathogen. What it gives you is the primary immune response, right? That whole week where you do the macrophage, and the helper T cell, and the B cell, the plasma cell, the antibodies. You do that week of cranking up the humoral immune system without really being sick. Now, this isn't virus only, right? You can do this with bacteria. But in the case of viruses, it's kind of our only real defense against them. The problem with vaccines has always been that they take a long time to develop and produce. If there's one positive from the coronavirus pandemic, it's that we've discovered that we can make a vaccine pretty quick. I think the record of getting a vaccine distributed or actually getting a vaccine approved for distribution before Corona was 4 years. So under a year is pretty good. Questions? Cool. One more thing. Oh, this is a good graph. You should probably draw this. You don't have to write everything. But here's what this is. This is your primary and secondary immune responses, whether it's a vaccine or you actually having the disease. Here's your week, right? Here's your week of, I guess here's your week of getting this humoral immune system to work and a level of antibody concentration in your blood, right? On your first exposure. This is enough to beat the disease back. And then you get rid of almost all the stuff. Get infected again, whether it was a vaccine or the disease itself, get infected again. Not only is the response faster, but it's way stronger. You get way more antibodies. So that disease does not stand a chance. Yeah. Yes, and I can't give you too many details there because I don't know them. This vaccine is not one that I know a ton about. I know it was produced in a way that uses RNA that's different from any vaccine before. And yeah, it does. You get a primary response and a secondary response. And I think the thing about the second shot is that not only does it give you a stronger response, but it makes the memory cells last longer. So I think if you only get the one shot, your immunity isn't going to last as long. I believe this is the case. Other questions? Okay, last thing is sort of a system, kind of a gold standard for proving if you've got a new pathogen and you think it causes a particular disease, this is the steps that you got to go through to prove it. Typically, this is done in animals besides humans, as you'll see the reasons for in a minute. But they're called Koch's postulates. I feel like geometry kind of gives postulates a bad name, but postulates are just steps you go through to figure something out. And so these are the standard steps to figure out if one particular microorganism causes one particular disease. You can honestly probably figure this out yourself. Let's say there's a disease going around in monkeys called monkeypox. And you think you found the green spiky bacterium that causes monkeypox. You think it's that one. What steps do you have to go through to prove that? How are you going to prove it? What do you need?
A healthy monkey, no. You're going to infect with the microorganism.
Do you need a healthy monkey and a sick monkey? Good, you have them. Now what do you do?
This microorganism that you think causes the disease is infected.
Okay. What's next?
You inject the pathogen, you have to forward the response
Where are you going to get the pathogen?
from the spiky cell.
That is the spiky cell. That's the pathogen you think it is. Where are you going to get it?
Blood.
Of? Good. So first, you got to get the pathogen from a sick organism. Great. You grab some blood from the sick monkey. There it is. There is your green spiky bacterium. Now what? What do you do with it?
Give it to the healthy one. It's
Okay, so you want to infect a healthy monkey with the bacterium. The problem with that is the amount you get from a blood sample typically is not enough to infect a healthy organism. How do you get more? Yeah, what does that mean?
All the children.
Bacteria are great that way. If you just put them in a dish with the stuff they like, they will make more for you. So you culture it in a lab, and then you've got enough to try and infect the sick or the healthy monkey. You infect the healthy organism, and that organism better get the disease you're looking for. So that monkey should get monkeypox. You might think you're done, but not quite. One more thing. How are we really going to prove this? How are we going to make sure? Basically, how are we going to make sure you didn't just pull some other bacterium besides the green spiky one and accidentally culture it too in your dish? And that's what made the second monkey sick. Yeah.
you got a lot of the second monkeys.
Okay, what are you looking for? If you're that advanced, or you could just look for, the green spiky bacterium, right? So you got to find it. You got to find that same microorganism in the blood of the second monkey that was healthy. Now it's sick. It should have a bunch of that microorganism you're looking for. And that's Koch's postulates. It's kind of the, if you want to prove it, that's the standard. All right. I have sample essays for you. They're a little shorter than normal. Because I'm eliminating 2 questions. So numbers 2 and 3, you don't have to do. I'll say that again once it's in your hands.